Because the brain is encased in the bones of our skull, neuroscientists have had to come up with some creative and complex methods to discover its structure and how it works. We will be discussing some of those methods and their applications in this video. First, it's important to note that each of these methods have pros and cons. One of these trade-offs is spatial and temporal resolution. Spatial resolution describes where things are happening in the brain. A method with a high spatial resolution will provide a clear picture of brain structure and location, just as a TV with high definition will produce a clearer image than one with a lower resolution. Temporal resolution describes when things are happening in the brain. Think of it like a piece of sheet music. Looking at it won't give you any idea about where in the room the music is coming from. You'd need to see the orchestra performing to know that. But you will be able to follow along and see exactly when and for how long each of the notes are being played by the performers. We'll discuss these concepts of spatial and temporal resolution a bit more as we go through each of the methods of neuroimaging. EEG, or electroencephalography, is a method where neuroscientists attach electrodes to a subject's scalp. These electrodes detect brain cell activity. When neurons are excited, they produce small electrical fields, and a large group of active neurons produce stronger electrical fields that are recorded and transmitted to a computer. Spatial resolution in EEG is very low, as data reflects activity of large regions under the scalp. However, temporal resolution is very high, as this electrical activity can be recorded quickly and accurately. You could potentially use EEG to measure electrical activity in the brain of sleeping subjects while simultaneously exposing these subjects to a previously conditioned odor. In a study conducted in 2012, researchers discovered that they could reactivate tasks while subjects slept by exposing them to an odor first when presenting them with the problem and then again while they slept. These subjects demonstrated greater creativity in their solutions the next morning than those who weren't exposed to the odor again. MRI, or magnetic resonance imaging, is a method where subjects are placed inside a machine that emits a strong magnetic field. In a normal state, the hydrogen protons inside the body's water molecules spin at random orientations. However, exposure to the MRI's magnetic field causes these protons to snap upwards, aligning with one another. Think of it like metal shavings on a table when exposed to a magnet. After this, a radio frequency pulse is produced from the machine, which pushes the proton's alignment aside in a predictable manner. This radio pulse puts the protons in an elevated energy state as it clashes with the magnetic field. When the radio pulse is turned off, the magnet causes the protons to snap back into alignment again, simultaneously releasing all the excess potential energy they'd been holding onto. This electromagnetic energy is then what the machine records. You could potentially use MRI to look at the brains of people who have experienced chronic sleep deprivation versus those who haven't and see if any significant differences exist in brain structure. An fMRI, or functional MRI, works in the same way, using a strong magnetic field. However, because an fMRI looks at brain activity, it measures the blood oxygen level dependent signal. Essentially, when certain areas of the brain are more active, the neurons in that area use more oxygen. Surrounding astrocytes in this area pick up on this increased demand and signal to nearby blood vessels to send more oxygenated blood. Because oxygenated blood has different magnetic properties than deoxygenated blood, the MRI machine is able to pick up on these changes in neural activity. This method has great spatial resolution, but it has low temporal resolution because the hemodynamic response is slow, taking several seconds after stimulus onset to take effect. You could potentially use fMRI to examine which areas of the brain are more active when individuals are engaging in creative tasks. Research, however, has revealed distinct pathways and networks of brain activity that seem to correspond with creativity and problem solving, as opposed to specific areas of the brain being responsible. A common neuroscience myth is that individuals are either left-brained or right-brained. fMRI could be used to dispel this myth by demonstrating that while some functions, such as language production, may be slightly more localized in one hemisphere of the brain, the vast majority of cognitive tasks utilize both hemispheres, working in tandem. TMS, or transcranial magnetic stimulation, works by sending magnetic fields into brain tissues to either heighten or dampen neural activity. Because magnetic pulses induce small electrical currents in the brain, it is believed that this method can change the firing patterns of affected neurons. TMS is often used as a treatment method for individuals with depression, as these magnetic pulses are meant to stimulate specific areas of the brain and thus change the brain's behavior in those areas. This method could also potentially be used to treat individuals with chronic insomnia by manipulating brain activity that inhibits individuals' ability to relax and fall asleep. TDCS, or transcranial direct current stimulation, works a lot in the same way as TMS, but instead of sending magnetic pulses into the brain to manipulate neural activity, it uses electrical currents. This method is similarly used to treat conditions like depression, and thus may also be potentially used to treat individuals who suffer from chronic insomnia by manipulating associated brain activity. Thanks for watching.